Let's start out by starting from that end and basically say, what are you going to work next? What are you excited about? Quick.
I'm really excited about translating the results we have into new devices that consumers can actually use to learn about their underlying health. I think that's really powerful. So really the translation of our research into real change in patients' lives.
Alex?
Like 100 different things. Like there's so many things. There's more science to do than there's like time to do it, right? I'm really excited about moving into clinical populations with our work, which I've never done before. I don't have any experience with, but I have great collaborators, and that's cool. Really exciting.
Yeah, that's a loaded question. There's so much to do. Two things I'm really excited about. So I showed a little bit of our clinical brain-computer interface work. One of the things we're trying to understand is, a lot of people have done speech BCIs, a lot of people have done motor BCIs. Ultimately, we want brain-computer interfaces that can restore all sorts of functions. So what happens when you're trying to do multiple things at the same time? Because it turns out, the brain is not just a bunch of isolated little centers, but there's a lot of crosstalk. So that's one. Two, with all the new interfaces that are coming out now, there's so much innovation kind of in the startup space. We're getting a different picture of the brain, with thousands of channels. So we kind of want to understand. So we've been have some work at SFN where we've been working with Neuralink to understand kind of what do you see different in those data.
I'm excited about behavior and linking passive behavioral measures to the passive neural recordings we get in our psychiatric DBS populations. There's been some work, but use that to inform treatment.
Yeah, I think as a clinician, I'm really interested in understanding the neural basis of cognitive processes, and especially when they're not working properly and they cause disorders like psychiatric disorders. I think the future really is, so the past, our past is studying neurobehavioral relationships in the operating room. We heard about that in the last talk, very powerful area to do that, but certainly limited. Then now we're doing a lot of this in the epilepsy monitoring unit with patients that are kind of around for days at a time. But really the next step is, like Nicole said in her talk, 99.999% of our time is spent out in the real world. So understanding the neural basis of how we interact with others, with the world, what the neural signatures are of being well versus not, I think are going to really inform, how we can deliver therapy, informed by that important piece of information, which is how we're actually doing, not necessarily how we're doing on a task or what we, say on a scale, but rather how we're actually performing in life.
So many interesting directions to go in. I rely on Samir and Nicole to help provide guidance. Some directions that I think are exciting from an ML AI standpoint is exploring the analogies between reinforcement learning and the human brain, which also does some sort of reinforcement learning, though far more complex. Getting to the basis, the neural basis or the psychological basis underlying OCD and the disinhibited states you saw. I'm also excited about, kind of a little bit unrelated to this, but could be related, is kind of what we talked about at the very end there with the, I'm sorry, Anton's talk. How do you use machine learning and AI? How do you audit that process, in this case with the lasso feature selection, but more generally with neural networks? How do you audit that process to extract actionable scientific insights to help drive future experiments and get at causal mechanisms?
I don't have an answer. Let's ask the audience if you have a question for any of the panel members, not me, any others.
Hi, when you say semantic decoders available for the public? Yeah. When is the semantics decoders available for the public or private?
We're not quite there yet. Hopefully, I don't know. In maybe a few years, it's possible to do this for a single person on a cheap budget using kind of off-the-shelf hardware. I'm hopeful for this, but it's going to be a little while to get there.
Okay, how to reach you for a license? Do you have any license right now?
So we're in the middle of like a patent application right now, but yeah, get in touch.
Thank you.
Any other questions?
While you have the mic, Alex, am I allowed to ask him the
Please,
question?
yes.
So, you know, you talked about the future, perhaps being, you know, kind of these household helmet, or kind of based decoders, prostheses, et cetera, right? So, do you think that the future? So, you've done, you know, the hemodynamic readout, and the DOT is similar. Versus electromagnetic with, I don't know, room temperature, MEG, et cetera. Like, where's the ceiling higher? Where do you think the future is brighter for, you know, being able to just like read each other's thoughts, like at home?
Yeah, this is a great question.
It's a very dark future, actually.
That's the worry, right? This is something we've thought a lot about. I think hemodynamic signals have a lot of advantages. They're big. There's like a lot of signal there, as opposed to electroencephalographic signals or MEG signals, which are quite small and hard to get, and you have to be very careful. Room temperature MEG, beautiful. You still need to be in a magnetically isolated chamber, which is pretty hideously expensive. Like this, you know, you don't need the MEG machine, but you still need something that is not like, you know, a normal kind of operation. A lot of people are trying to push similar technologies with EEG, and I'm a bit skeptical. Like I have worked a little bit with EEG data. Maybe it could work. I would be a little surprised if things worked like very well with EEG, but it's
That's what people said about fMRI.
Exactly. People have said that about fMRI too. So it's like I can't say that won't work. Yeah, and this seems to be kind of as far as we can get with non-invasive approaches. Maybe physicists will come up with some new fun way to measure brain activity that relies on some principle that we just don't know about yet. That would be fantastic. If there are any physicists in the room, like, please do that. Like that we really want this. We need this. That would be great. But then I think there's also a spectrum of invasives that are kind of exciting. So y'all have talked about these, you know, DBS electrodes or implanted like grid electrodes, this kind of thing. Something that seems to be coming, and it's unclear how useful it is, but it could be really exciting, is the intravascular electrodes, the stentrodes that are placed not via like brain surgery opening up the head, but via like angioplasty type surgery, which is less invasive. I don't know. That kind of thing I think is exciting. I think there's going to be a lot of innovation in this area and new things opening up.
Roy.
Yeah, this is a question for Dr. Huth. I didn't get to ask it at the end of your talk earlier. But as you saw from Dr. Banta's talk, our group is interested in a variety of modalities. So I wanted to ask if you could pick one or two other modalities to complement fMRI, because as you mentioned, fMRI has strong temporal limitations. What modalities would you be interested in?
For what?
To improve the performance of your current I guess, language decoding or encoding models? Yeah,
so we've done some work, like the kind of obvious answer is something low spatial but high temporal resolution, right? So complement fMRI's strength in very high spatial resolution, but kind of crappy temporal resolution. We've done a bit of work on trying to do fusion between fMRI and EEG data. So we collect like match data sets in the two and then try to build models that relate the two. That's hard. It's like it's really hard. We haven't gotten a lot of good results out of that. I don't know. That's a good question. I think one thing that is going to be surprising going forward is that there's actually more information in the fMRI signal than we expect, and more information especially about fast events. And if we have good computational models, we can pull these things out, kind of do temporal super resolution and pull these things out in ways that wasn't possible before. That's not a different modality, but I think that's one direction that we're kind of going that I'm most excited about here.
Thank you. And then a follow-up for the panel, just based on that response. Given I guess the challenges of recording and analyzing multiple modalities, I'm curious what you all think are some of the big challenges to overcome in that space, or if you think that focus should be made on improving single modality processing over integrating different ones.
I can go first. Well, one is obviously the timing, the time resolution of different signals and what it tracks. So there's something like GSR, galvanic skin response. There's always a delay in that versus like the underlying process versus EEG, which is, immediate response to certain processes. So combining things across time is complicated. But there's also, again, the biggest problem, I think, especially if you're trying to use it for machine learning models, is collinearity, or when things are codependent. So you may think that you have this modality and this modality, you get these features, and you're like, oh, these are all different ways of viewing the body. But everything is so interrelated that you can actually make your models much worse if you give all of these features, because everything kind of can move together. So you have to be very careful about how you extract useful information from different sources.
Oh, yeah, I'll give it a shot. Great question. So I'll talk about it from the brain-computer interface standpoint. One of the things we often think about are spiking activity, like I showed in my talk, and more field potential-like activity, like continuous features. There are a couple practical challenges when you start to combine them. One is like when you think about how a brain-computer interface really works, some of it is like the decoding stuff that I talked about, and then a lot of it is the person figures out how to get it going, right? Like I think as Alex was saying, people are good at adapting to things. Like if I give you something to hold, you can do a lot of cool things with it. Like instantly, you can adapt to a new plant. And so partially we want to like maintain flexibility to give the people tools to adapt. But then when you think about combining signals that have very different like time constants, it becomes a harder control problem for the person if like, one signal is really responsive, one signal has a big lag, and you're, kind of pushing in different directions. So yeah, there's some practical challenges there.
I have two things to add to that. One is before you can like analyze the large data set, you have to store and organize it. And I think a lot of like academic labs kind of struggle with this because a lot of us don't have data scientists working for us around the clock. So it's like, an art in and of itself, I think, to like put your data in a database and make sure it's queryable and searchable so that you can use it productively, especially when you're recording around the clock in many participants. So that was one big challenge. And then the second one is on the other end. What do you do when like data from two different modalities disagree with each other? Like for example, we talk about, what if the patient tells us they're doing great, but their clinical assessment tells us they're doing badly, or their objective behavioral measures says they had a bad day. How do you reconcile those two things? Or what do you do when the content of what somebody is saying is like really positive, but the way they're saying it is like really, dreadful? So I think like kind of making sense of data that disagrees with each other is going to be a big challenge.
I have an ill-posed question for Chetan. I've been trying to just figure out how to ask this. So, those like standardized tests where you have like a list on the left and a list on the right, and you have to like match things. So imagine that. So on the left, you have, non-invasive stuff. You have Alex's hat that's, going to be his retirement plan that reads thoughts. And then you've got a little more invasive, you've got the synchron, then you got the, maybe the cerebral, but extracortical, and you've got your intracortical. So all those things, right? All the different BCIs. And then on your right, you have therapy and you have enhancement. Which ones on the, what in the left is going to best match either of those on the right?
Ooh, that's a really interesting question. I guess the need for different levels of invasiveness is, I think, very much application dependent. Enhancement, we're really good at things, right? Like, I mean, people, can do things quickly. We can adapt. So, like, to to do stuff better than people, you probably need a fair amount of information at high resolution. Like I'd be shocked if you can do kind of enhancement with non-invasive interfaces. I mean, sorry, there are some things like there are likely ways of, kind of stimulating the system and kind of driving up plasticity or things like that that might work well kind of non-invasively. But something that kind of involves interacting with the outside world at faster than human speeds, it feels like it'd be really hard to do that non-invasively. Is that along the lines of where you?
Wires in the brain.
Yeah.
Little threads.
Yeah, threads are pretty good for that.
Yep. Caleb?
So on this topic about enhancement, I think one of the most interesting fronts of neuroscience is like that it's getting at like addressing these like probably the most deep and the most weird philosophical questions. So I was wondering if any of y'all had opinions or thoughts on like how your work in neuroscience is is it leading towards like is it changing your representation, how you think of, I guess, the origin of sensation or the origin of action? Yeah.
I think for sure it originates from the brain. But if you're getting at conscious perception, emotions, things like that, so from a therapeutic standpoint, it would be great to figure out, for example, how mood is encoded in the brain, especially for folks with psychiatric disorders or TR, treatment-resistant depression, et cetera. But I think you're probably delving more into the philosophical side of things, like what, qualia and what is the, first-person experience. Is that where you're going with this, or? Yeah. Yeah, there's still a big conceptual barrier to go from third-person descriptions of a brain and first-person subjective experience. So I'll need a little bit more time to answer that question.
I can say something about this. Not exactly the questions you asked, but my work has made me rethink really what language is and what the relationship between language and the brain is in a way that I think I would not have expected years ago. So a way that I like to think about this is like, what are the set of brain things, brain operations that you could not elicit through language? And I think that set is pretty small, actually, right? I think many things that you can think that you can do with your brain, you can make a brain do by saying the right words, right? Saying like the magic incantation that makes you sad or makes you happy or makes you think of driving your car or whatever, right? Like so many different cognitive things like we can turn on with language. And it turns out that this is really kind of reflected in how the brain responds to language. So really, as opposed to these classical views that there's a couple language areas in the brain, what we really see is that a majority of the cortical surface does something with language, responds consistently to some property of language. And I think this is really because language touches everything cognitively. It touches almost everything, right? You can't turn on V1, you can't turn on like primary motor cortex just by saying words unless you tell someone to move, I don't know. But most, like, any thought you can think we can express in words and you can put into somebody else's head using language. And I think that's cool and interesting.
In a slightly different direction, I think one of the things that we're gonna have to be really careful about when we're working on these brain-computer interfaces, especially for language, but also for movement. So for both of those, I can think about moving and not attempt to move, or I can think about speech and not actually intend to speak out loud, right? And we definitely see both of these things even in what you would consider kind of primary motor areas and premotor areas as well. So, you can think about kind of what is the intention to speak? Like, where exactly is that line between like just thinking a thought and actually, wanting to convey that thought? and how do we, very carefully for people with these implants, prevent kind of private things from becoming public. One of the things we see is, so I showed a little bit where our participant is attempting to speak, and we decode, and we've been doing some sessions where if something is wrong, she can kind of go back and select the words that are wrong and pick from different options and correct them. But one thing we realized is, like, during that process, we have to give her the option to turn the decoder off, because as she goes back and reads through things or sounds things out in her head, it'll continue to just decode those things. So we might get the same sentence like over and over again, and she's obviously not trying to speak it. So yeah, like kind of understanding that boundary between kind of intention and just internal thought is going to be really critical.
Question?
Yes, I have a question from the student's perspective. So I was wondering, like, from your personal experience, what kind of, if you have chance to do it again, what kind of skills or experience you wish you have, like, when you were taking classes as a student, or maybe another perspective is, like, what kind of skills you guys are looking for if I want to enter into your field? That's why I was wondering.
What I always tell people is, this is whatever niche, linear algebra and signal processing. These are the two things. Electrical engineers often have this combination of things. Weirdly, a lot of other people don't. I work with, a lot of computer scientists who, strangely, signal processing is just not a part of the NECS curriculum, but it's a really big part of what we do. So those things and statistics to some extent are like the really core to our work.
Yeah, related during the breaks, there's an undergrad here, like freshman, who is wondering about what she should take, and like should she go down this path versus this path if she wants to work in the field. I think like as an undergrad, I was studying like solid state physics and computer engineering, like nothing to do with what I do now. But I think there's no substitute for kind of deep technical training. It's hard to make that up. The other thing that I think is really helpful, honestly, and I kind of recruit this in students, is like a fearlessness. Like nobody knows everything you need to go into this space, but just a willingness to like not be bothered by the fact that you don't know and just go and learn something is really, really critical.
Those are all really good ones. I'll add what Ankit said earlier about understanding the application space. Like, first I think you have to have a solid technical training, but then you really have to understand why you're solving the problem that you're solving and where the data is coming from. I think there's nothing like collecting your own data to help you understand how to analyze it. So that's important. And then just work ethic and curiosity.
I wish I had taken more biology and biomedical courses, actually, because I just stocked up on physics and CS and math and totally ignored biology in undergrad. So I wish I had done more of that.
You'll be fine. Now, I have one last question. Is that right? All right, I have one last question for the panel. We all know that if you give me 10 million pictures of a dog and 10 million pictures of a cat, I can build a system that classifies them, right? A lot of N, big N, right? Now, as I think Anton mentioned, in our little world here, we don't have big N. But there are some techniques in machine learning and data science world that overcomes that limitation. What is your favorite one that I know what Anton's is because he just mentioned it, but how about others?
I'm going to go to, I think this is Jan LeCun's analogy, unsupervised learning of data sets. Like even if you don't have big labeled data sets, if you can find big unlabeled data sets and then use unsupervised or self-supervised, whatever, target-free learning to learn the structure in that data, then doing something useful with it is just whatever. His analogy is that unsupervised learning is like baking a cake, and then supervised learning is like the frosting on the cake, right? Reinforcement learning is the cherry on top. But you need, once you have a good model of the statistics, the structure of something, you don't need much data to fit good supervised models. This is what language models, this is why large language models are so good and so important and whatever, is because you can just feed them almost limitless amounts of data because they don't need to have labels, they just learn from the structure of the data.
Yeah, one of the things that I've been really excited about lately, some folks in my lab are working on diffusion models and information-based diffusion models where you can create kind of generative models that have sort of interpretable latent spaces. And the reason I'm really excited about it is because you can train on data sets, but then kind of push to different areas of your latent space and generate samples that correspond to uncollected data. And they actually do a reasonable job of both interpolation and extrapolation. So I think there's a lot of opportunities that come from that kind of synthetic generation approach.
Chetan stole my answer, so.
Yes.
I'm actually very interested in understanding, so we talk about the black box, especially in the context of neural networks, but it's actually, unlike with more traditional machine learning models, where we kind of know the biases, the inductive biases, because we program them in, right? Like we saw in Anton's talk, the L1 versus L2 regularizer. We understand that pretty well. We can strengthen it or weaken it. But inside neural networks, we actually don't understand the regularization process that's going on. In fact, it has a fancy name. It's called implicit regularization, a euphemism for, oops, we didn't realize that was happening, but hey, cool. So I would like to understand that a lot better, extract those regularizers, make them explicit, and then try to control them the way we do Lasso and others.
Is there time for another question, or are we done?
One more question, yes.
Well, I had a question, especially for folks here that have been doing more interfacing with kind of the clinical world. You know, to get these kind of smart neuroengineering systems where we can really start running some powerful models in closed loop. I'm just curious if you think what's going on the clinical side is there enough like innovation that's going to kind of support some of these exciting applications? I tend to think of a lot of like kind of traditional neurotech companies as a little bit slower to innovate. Do you see like room for AI in this space, like in a practical kind of clinical deployment that standpoint?
Yeah. So like a couple examples. Medtronic is running the ADAPT PD study to test closed loop stimulation in Parkinson's disease, and I don't think they've published the results yet, but my inkling is that it's positive. There was a recent study from Phil Starr's lab at UCSF looking at adaptive stimulation using a research device, whereas the ADAPT PD is their commercial device. And in the research device study, they actually were able to like improve symptom control and improve quality of life in the patients that had adaptive DBS. So I do think that will open the door. Medtronic has also been pretty interested in our study, and we're looking for ways to kind of like improve device functionality so that it can be more amenable to doing closed loop on the long time scales that we're looking at in psychiatric disorders as opposed to the short time scales in movement disorders. And then there are other companies like Abbott that are really interested in like using behavioral like data from wearables to inform treatment changes. So like I'm optimistic that it's like happening. I definitely think it's slower in industry, but also industry helps us like make it broadly available. So like I think both are important.
Yeah, also a strong yes, and I'll add two things. One is, you can ask a question like, is there information in neural data that you can get from these devices that is diagnostic? Well, of course, yes. Okay, absolutely. Is that information in the context of understanding what healthy versus unhealthy looks like? Does that help you choose what to do, how to intervene? Almost certainly yes, right? So this information will definitely improve how we understand a disorder and what we should do to treat it, because otherwise it's very empirical, right? All of medicine is totally empirical. Our actual data good data in randomized trials is very minimal, right? So a lot of what we do is empirical. So this will bring it, a little bit more data-driven. And the second part is, as these systems get more complex, I'm talking about clinical systems that are used to treat disorders, it takes way more time than any particular clinician has, right? So they need something to assist them. How do you explore this vast parameter space? Your DBS systems used to be simple, now they're super complex. Nobody has time to trial and error, brute force their way through this. So they need help. They need systems to be able to, explore that parameter space and tell them, this is what you need for this patient with Parkinson's or OCD or depression. So that is going to be super critical. As the complexity of the system increases, the devices increase, the intelligence has to increase in order to keep, healthcare deliverable.
My group is obsessed with nonlinear data-driven control. It's not an easy problem, but it is. We're heavily invested in working that. Now, if there are no other questions, let's thank the panel.